Hi, and welcome to Failurology, a podcast about engineering failures. I'm your host, Nicole.
And I'm Brian, and we're both from Calgary, Alberta, Canada.
Thanks again to our Patreon subscribers. As always, we really appreciate your support. And we also love chatting with you and nerding out about all of these really interesting engineering failures that we're talking about.
Our Patreon costs less than 4 boxes of Kraft dinner. For our non-Canadian audience, that is macaroni and cheese. Less than 4 boxes, you can have some great engineering content that is not available on the regular platform.
So that's $5 Canadian a month for twice as many interesting engineering failure episodes. And that price is not going up because our bonus content is inflation free. So that is $5 now, and it's going to stay $5. And if you're not from Canada, it's probably less than that because our dollar is not super strong right now. And so it might only cost you $3 or $4 in the country that you hail from. So please come over there, support our show, check out our extra content. We have a ton of episodes over there. I think we're, if not quite at 30, we're almost at 30 episodes. We've been releasing some of them on our regular feed whenever we needed to take a break. So I think we released 2 last summer and 1 a couple episodes ago over the Christmas break. And so if you want to hear what those sound like, you can check them out that way. And then you kind of get a feel for what they sound like. And on our website, failurology.ca, we also publish a list of all of those mini failure episodes. So you can see what we've talked about over there and if there's any that interest you before you dive in. So that, I like to know what I'm buying before I buy it. And I assume you guys do too. So we've done our best to provide you with that information before you jump onto our Patreon bandwagon.
For those of you out there listening, it might seem like we've been recording continuously because we followed our regular podcast schedule for episode releases, but what you may not know is that we recorded all the episodes over the holidays, or the ones that came out over the holidays, in November, and then we took 8 weeks off, which was great.
It was so great.
So this is our first episode back after our, I was going to say little break, but it was actually a fairly long break. I think that's the longest break that we've ever taken between recordings. So if either of us seem rusty, that is why. And if we seem a little awkward or more awkward than usual, it's not our fault. We're engineers.
Yeah, I think we're all a little awkward already. So this is just a little extra. That break was really nice. I've said this before. I love making this show. I enjoy all parts of this show, but sometimes it does get to be a little bit much. And so, we had to work really hard to get ahead far enough that we could take that break. So there was some weeks where we recorded extra, and there were definitely weeks we didn't take off so that we could make sure we stayed far enough ahead that we got that break. And it was really nice to just step away, relax, enjoy that family time over Christmas, be an introvert and not leave the house for several days before New Year's, and then kind of step back into the swing of things here in January. So the break was great, but I am really excited to be back.
I also echo all of those things that Nicole said.
This week, in the goings-on of engineering and other things, gelatinous animals are inspiring underwater vehicle design. This is a really interesting article, and it's got some words I'm going to mispronounce, so sorry in advance. Nanomia bejuga, which are related to jellyfish, and I shall, going forward, refer to them as the jellyfish-like things, because that word I think I'm mispronouncing. They use these little jets on their body to push water backwards, which moves them forward. And the cool thing about this is they can control all the little jets individually or all at once. So they can prioritize whether they want to go really fast or whether they want to have control and efficiency over where they're going. Researchers at the University of Oregon are using this discovery from these jellyfish-like animals to build more robust underwater vehicles. And so far, the research found that most underwater animals are either fast or efficient, but not both, like these cool little creatures. But these guys, like I said, they can do both. And the weird thing is they don't even have a central nervous system, which, being the non-biology person that I am, I'm assuming that that's an important part of a biological organism. And these guys don't have one, and they're still able to control all these little jets, which is pretty cool.
Yeah, that sounds super cool. I'm also not a biology person. I had wanted to go kind of the med school route when I was in high school, but then plant biology in grade 11 just kind of sunk that career for me. So I never did biology in grade 12. So I get to learn about all these exciting biology things, and I don't know what some of the words mean. So these guys, they use 10 or 12 of these jets to get around, like Nicole mentioned, and each of these acts like an individual unit. And they have tentacles on them for food, reproduction, and defense-related purposes. And when all the jets move together, or when all the jets work together, these organisms, they move super quickly. But if the jets work separately, they move much slower, but they're a lot steadier. So researchers are obviously hoping to apply this method to underwater vehicles to allow them to have a range of functions. I think this is super cool. It reminds me a little bit of like bow thrusters and various thrusters that they have on ships for maneuvering for docking purposes. But these would be for underwater vehicles, which I think is really, really cool. I don't know if this falls into the mimicry category of where humans are mimicking or taking a lot of design features from things in nature. I know we've seen this a lot before with the kingfisher and the shape of bullet trains. There's a lot of stuff out there in nature that's evolved over the last number of millions of years. And I always think it's really neat when we can take stuff from nature and incorporate it into making human stuff work a little bit better. If you want to read more about these really interesting jellyfish-like things and how they get around, check out the link on the webpage for this episode at failurology.ca.
Tired of washing dishes?
Dishwasher broken?
Flip the dishes over. There's a second side to those.
At least the plates.
We can't help you out with the bowls, but if it's the morning and you have no bowls, you're already in a bad spot if you wanted cereal.
Use a mug or something. You're probably still half asleep anyway. Who's gonna judge you for eating cereal out of a mug?
We got your back. Flip the dishes.
Now, on to this week's engineering failure. This Sayano-Shushenskaya Hydroelectric plant. Just a warning, we are going to do our best on the pronunciation of words in this, just like the jellyfish. We've practiced a number of words ahead of this recording. Can't promise that we're going to get them 100% correct. Likely still screw them up. We're sorry, but also not super sorry.
We're trying here. As someone who watched a lot of GoldenEye as a kid, I do feel slightly more suited to be able to pronounce some of these words, but Russia also uses a different alphabet, so that just throws a whole nother level of complication into this.
Located on the Yenisei River near Sayanogorsk, which is in southern Russia, about in the middle of Russia, near the border of northeast Mongolia, which, just as a side note, Russia has actually the second most time zones out of any countries in the world. They have 11, which is right behind France, which I'm sure most people wouldn't expect France has a bunch of time zones. France has 12, but those time zones are because of a lot of their overseas territories and protectorates and kind of comes from colonial times. So if you need an interesting Jeopardy or trivia fact, there you go. 11 time zones for Russia, 12 for France.
That is fascinating. I find time zones in general to be really interesting. I know that sounds weird, but just how I get it. They have to pick somewhere to draw the line, but just that when you cross this line, the time is different. It's just fascinating. And then, being in Alberta, we're almost at the end of the day. So I think Hawaii is the furthest that you go, but then if you keep going west, it's tomorrow. And so it's weird that right now it's tomorrow somewhere else, and that's just a weird thought to think about. I don't know that.
Actually, Nicole, did you know that time zones were actually invented by a Canadian?
I did not know that. Also another fun Jeopardy fact.
Time zones were actually invented for railway times, or for railway schedules, because before time zones existed, most people just said they'd look up and, it would be 12 o'clock in a local time. But as Nicole mentioned, I mean, obviously, the Earth is rotating and it's technically different times in different places. So time zones are divided every 15 degrees of longitude is where the time zone boundaries change. But within that time zone, even though throughout the time zone the time is still the same, there's actually what's known as a local hour angle. So throughout the time zone, there's a couple minutes of difference, whether you're on the east end of the time zone or the west end of the time zone. And obviously, as railway traffic picked up in the 18th century, it was really important for the trains to run on time and people to know exactly what time it was, which is how Sir Sandford Fleming came up with the concept of time zones. And he is Canadian. I believe there's actually a college in Ontario that's named after him. I'm not sure what sort of technical work they do there. But yeah, time zones were invented by a Canadian.
Very cool. Very cool. Yeah, time zones are cool. Daylight savings, not cool. But time zones in general are cool.
The dam has had 5 significant accidents. For this episode, we're going to focus on the 2009 one, but we'll still tell you a little bit about the others. But before we get into that, we have to talk about the dam, its construction, how it operates, and obviously some of the limitations for the dam. So the power plant in the dam, it's the 12th largest hydroelectric power plant in the world at 6,400 megawatts.
And at the top of that list, the largest hydroelectric power plant in the world is the Three Gorges Dam in China. And that dam is very interesting. We're going to talk about it in a future Engineering Marvel episode. That Three Gorges Dam has a capacity of 22,500 megawatts. And then also the Itaipu Dam on the border between Brazil and Paraguay is also high up on that list. I think it's number 2. Most of the dams on the list of the world's largest hydroelectric power plants come from China, Brazil, Russia, and then a bunch of other countries are on the list, but those I would say are the big players. And also on that list is the Robert Bourassa and Churchill Falls power plants in Canada and the Grand Coulee and Bath County plants in the USA.
The power plant in the dam, it's hydroelectric, obviously, which means that it uses flowing water to spin a turbine and generate power. A lot of power generation basically consists of moving a fluid or moving a gas over top of a turbine and making it spin and then generating power through that. In this case, hydroelectric, hydro obviously means water. So it's water that passes over this turbine to generate electricity. And this includes a dam to hold back and direct the water to the turbine, obviously. And then the type of the dam, it's an arch gravity dam, which is the same style as the Hoover Dam in the USA, just outside of Las Vegas. So in the dam, there are 10 turbines, and they each have a capacity of 640 megawatts, and these sit in cavities in the machinery hall located at the base of the dam. The pitches of the hall, they remind me kind of a nuclear power plant because you just see the tops of the turbines, similar how you just see the tops of the reactors in nuclear power plants. This dam is fairly large. Actually, I'm going to say it's really, really large. It's 242 meters tall, over 1 kilometer long at 1,066 meters, and 25 meters wide at the top and 105.7 meters wide at the base. Like, that is a massive, massive structure.
So the dam, as they do, create a reservoir. This one's called the Sayano-Shushenskaya Reservoir, which has a capacity of over 30 cubic kilometers of water and a surface area over 600 kilometers square. So for comparative reference, the surface area of Calgary is 825 square kilometers. So this reservoir is about 75% the area of the city of Calgary. And I've talked about this before. I won't go down the whole rabbit hole, but Calgary, we just keep eating jurisdictions and towns and small villages as we expand. So there is no greater Calgary area with all these different municipalities. It's just Calgary. We are all one city. And so that it's a large city, and 75% is a large reservoir.
Yeah, this is basically a rectangle that's, say, 20 kilometers by 30 kilometers. Like, this is not a small reservoir in this dam.
Yeah. So construction of the dam began in 1963, and the first turbine was started in 1978, and the dam was fully operational with all 10 turbines running in 1985. More than 70% of the electrical power that's generated from this dam goes to serve 4 aluminum smelters in Siberia, which is just north of where this dam is located. And the smelters are used to heat ore and extract aluminum. It's important to note that smelters have rapid and unpredictable load changes, which the plant had to accommodate. And that's not the reason that the dam failed, but that's definitely going to play a factor into how catastrophic the dam failure was. The dam was federally operated, but it was privatized after the collapse of the USSR in 1993. And for the younger people listening, the younger millennials and Zoomers, Russia used to be not Russia. It was called the USSR. It was much larger, just as terrible, probably more terrible. And it's just a really fascinating point in history that's not really relevant to this failure or this show, but something I definitely recommend checking up on and reading about if you are not familiar with this, because it's an interesting story.
The next part I think will be interesting for all the mechanical and civil engineering minded folks. The dam is said to safely, and I use air quotes when I say safely, so safely withstand earthquakes up to an 8.0 on the Richter scale. So although it was recorded into the Guinness Book of World Records for being the strongest construction of its type, the word safely is in quotations. And if it's Russian built, it should probably always have safely in air quotes there. So take that for what you will.
Russia seems to like to keep up with the Joneses a little and sometimes exaggerate or not be fully forthcoming. And so I don't really know. It's never experienced that type of earthquake. We don't really know what it can withstand, but that's what they claim it can do.
So there's 30 million tons of water pressure that are applied to the base of the dam. And this is over 3 billion with a B, kilopascals, and over 67 billion PSI.
So in my work in mechanical engineering, which is related to buildings, I rarely deal with more than 300 PSI. So 67 billion PSI is a whole lot of pressure.
Done a number of projects in oil and gas on the pipeline side of things. One of the projects I worked on, it was over 2,000 PSI for pressure in a pipe. Even at that, which was one of the highest gas pressure lines in Canada, this dam has way more pressure that's acting on the base of the dam than very high pressure gas lines. So this 30 million tons of water pressure applied to the base of the dam is supposed to be split with 60% neutralized by the dam's weight and 40% carried to rock that's on the bank.
But in 1998, the Russian Emergency Situations Ministry claimed that the, quote, station construction had dangerously changed, and that if pressures continued to increase during spring floods, the dam might not be able to withstand those higher pressures. So based on the location of the dam, I imagine the river that it's located on sees spring runoff as the snow that's accumulated during the winter starts to melt. And we have a similar situation in Calgary. It can be really tricky to manage because you don't really have control over how it snows or where it collects or how it melts. This is usually compounded, especially in Calgary, if the melt coincides with rainy season. And that's why we call affectionately sometimes June is monsoon June, because it rains and we have the melt, and sometimes it can be really bad for our river, like it was in 2013. If you just look at the water management aspect of the dam, ideally you would lower the water levels before the melt, and then you continue to shed water through the spillway to keep the levels at a reasonable place while looking upstream to see what's coming. And that's what they do in Calgary now. They lower the reservoir levels. I mean, our dam is nowhere near this large, but they lower the reservoir levels ahead of the melt, ahead of the rainy season, so that they're prepared. If they get a big influx of water, it doesn't overwhelm the system. That said, from a power generation perspective, any water that's sent through the spillway is wasted energy potential. And so you don't really want to do that unless you have to. So from that angle, you want to maximize your power generation, and you don't want to divert any water through the spillway. And I think it's a balance. You need to prevent it from being overloaded, but also try not to shed any water that you don't need to. And I think it's a bit tricky to manage. This is also my very high level understanding. I imagine in reality it's a lot more complicated and takes years of experience and practice to master. I don't work at a dam. I've never even designed a dam. I find them really interesting, and that's why we've done a number of dam failures on this show, because I do find them really, really interesting, and this would be my understanding of how they would manage this. But yeah, I imagine in reality it's very much more involved.
The basement of the dam had weakened between the original construction in 1978 and 1998, which is only 20 years, and that's not really ideal. I mean, this is something that should have lasted a lot longer, especially for something that is earthquake resistant. Unfortunately, the weakened basement meant that the 30 million tons of water pressure wasn't being divided as intended, so that 60-40 split, that wasn't happening. And it's estimated that most of the water pressure and some of the dam's weight was actually being applied to the shore rocks. There were also issues with water infiltration or water passing through the dam's concrete, which we've definitely talked about on previous episodes. And we've seen this as a common occurrence in earthen dam failures. And I'm actually really surprised that it didn't lead to failure here. Luckily, in 1993, a French company injected resins into the dam and it worked to reduce the water infiltration. Russian companies, they were able to repeat the exercise over the years as needed, which I think is really good for preventative type maintenance. And the soil under the dam was also injected with resin to mitigate water infiltration.
In 2007, the dam was audited and it was determined that 85% of all technological equipment needed to be replaced, which sounds very expensive. In addition to the dam's structural concerns, the spillway was undersized to handle the spring melt, which is unfortunately not surprising. That seems to be a thing that happens a lot, which is really frustrating. They should just start oversizing these and then maybe they'll be the right size. The spillway could handle up to 7,500 cubic meters per second, but it was limited to 5,000 cubic meters per second after it had experienced extensive damage during a previous spring flood, which takes us to the earlier failures before the catastrophic one in 2009. That's the main topic of this episode, and we promise we are getting to that shortly. In May 1979, spring floodwater entered the machine hall, which is where the turbines are located, and flooded the first working turbine. And this happened while the dam was still under construction, which would have been a great time to correct some of its issues. In 1985, the spring flood destroyed 80% of the concrete spillway's bottom plate and tore apart 50 millimeters or 2-inch thick anchor bolts and carved 7 meters deep into the bedrock, which is why the spillway capacity is now reduced. And then again in 1988, another spring flood destroyed the spillway as well. So there's been a lot of damage from spring floods. A lot of them seem to be because the dam gets overwhelmed and the volume of water going down the spillway is much larger than they're rated for. And again, I'm not a dam operator. I'm not qualified to make this statement, but I'm still going to say it. Maybe you should lower the water levels before the spring flood happens, and then you would have capacity to take on this extra water. Maybe it's possible that could work.
It seems to work pretty well in other countries in the world and on other dams, so probably something they should have done. I don't know the circumstances around it, why they didn't, but unfortunately that didn't happen. So as you can see, the dam has a number of issues. It appears that it either wasn't as strong as it was supposed to be, or the designers of the dam did not account for the heavy spring melt. Reality is, it's probably somewhere in between the two. I'm not sure what one had more influence. And the spillway was undersized, which we've seen before, and unfortunately seems to be a fairly common issue in dam designs or in dam failures. Maybe not the actual capacity of the spillway itself, but one issue or another with the spillway seems to lead to the dam being too full, and then it either collapses or it overtops. How this dam is still standing, I'm not really sure. In fact, it's still in operation. If you were thinking about moving to this area of Russia, maybe try to find a place upstream of the dam versus downstream of the dam. I'm not sure how much more life this dam has left in it. So upstream, probably better than downstream if you're looking to move to Russia.
So a friend and I were talking about bad system designs, and he told me about this Simpsons episode that I think is relevant to this dam and also probably relevant to some of the other failures that we've talked about. So in the episode, Mr. Burns goes to the doctor and he's told that he's the sickest man in America, but that all of his diseases are in perfect balance. It's like they're all trying to get through a door that's too small, and therefore none of them can get through. And Mr. Burns says, "So what you're saying is I'm indestructible." And the doctor says, no, a slight breeze could kill you. And that's what it feels like when we're talking about some of these failures. There are so many things that are wrong that they almost start to work together to hold this house of cards together. And I am shocked that this dam is standing. Shocked.
With that said, on to the piece de resistance, the 2009 failure of this dam. So this was surprisingly not the result of spring floods, water infiltration, or water pressure, or really at least not directly. So on August 17, 2009, Turbine 2 catastrophically failed, flooding the turbine hall and collapsing a portion of its roof damaging or destroying 8 of the other turbines. So for those of you counting along at home, that's 9 turbines that have been damaged. There's only one left that is not damaged. Unfortunately, this also killed 75 people. The turbines, they have a narrow working band of high efficiency regimes. If the band is exceeded, the turbines vibrate, cause pulsation of water flow and water strokes, and the turbines degrade over time.
So Turbine 2 had issues pretty much since it was installed, and in the early 80s there were problems with seals, shaft vibrations, and bearings. In late 2000, they rebuilt the turbine and found cracks 12 millimeters deep and up to 130 millimeters long at the runner, which is the part of the turbine that catches the water and transfers that rotational force to the generator. These were repaired, and similar degradation was found again in 2005 and repaired at that time as well.
In early 2009, 5 to 7 months before the failure, Turbine 2 was undergoing more repairs and also a modernization at the same time. It was the only turbine to have an electro-hydraulic regulator of the rotational speed. Also repaired were the turbine blades, which were welded to correct cracks and cavities. Unfortunately, the runner was not balanced after these repairs, which anyone dealing with an unbalanced rotating component knows. This is bad news bearings. It's like when your washing machine load gets unevenly distributed and the washer barrel makes that clunking sound as it goes around. Imagine that on a turbine larger than your house. That is a lot of clunking, and it would be loud. So the vibrations that occurred as a result of the unbalanced runner were within specifications at the time, but not ideal for long-term use. Kind of like your washing machine if this happens to it. As the turbine remained in use, the vibrations exceeded specifications in early June, and they continued to get worse.
Between August 16th and 17th of 2009, the turbine vibrations increased substantially, and the load was increased and reduced several times, as well as unsuccessful attempts to stop the turbine. In a comedy of errors, on August 17th, the plant's general director was off-site to celebrate his anniversary and greet guests. I believe it's his work anniversary, and no one else at the plant had the authority or wanted to make decisions about the turbine, and so they just left it operating as is with the high vibrations. At the time of the accident, Turbine 2's capacity was about 475 megawatts, which is definitely not max load. These can handle 640 megawatts, and the water consumption was about 256 cubic meters per second, which, if I'm being completely honest, doesn't mean a lot to me because I don't know what that normally would be. The vibration was about 4 times more than any of the other turbines, and at that point it had greatly exceeded specifications. The turbine was 29 years and 10 months old at the time, with an expected working life of 30 years, and that came from the manufacturer. So that's, I think, really interesting for it to be so close to its expected working life when it failed. It's usually not quite that dramatic. And I will say the working life expectancy of equipment it's usually a guesstimate, and a lot of equipment, especially if you take care of it, exceeds that time frame. I typically recommend that you look at life expectancy as a way to budget for replacement work, but it's definitely more cost effective to keep things running as long as you can before replacing them. But also don't wait till the middle of winter to try and replace your heating equipment. That seems like a really bad idea because you might not have heat, and that would suck.
At 8:13 a.m. local time on August 17th, there was a very loud bang from turbine number 2, which is never a good sound to hear from really anything. The cover of the turbine shot up and the 920-ton rotor shot out of its seat. There was nothing to hold back the water, and it spouted from the turbine cavity into the machinery hall, flooding it and all of the rooms below it. So the power plant, it obviously went into an alarm, and the output dropped to 0, leading to widespread blackouts. The water gates to the turbines were manually closed, which took 25 minutes and was the fastest speed allowed for that operation. 25 minutes still seems like a really long time for these water gates to close. An emergency diesel generator was started 3 hours and 19 minutes after the turbine failure to open the spillway gates, which also seems like a really long time.
One of the survivors said this about the accident. I was standing upstairs when I heard some sort of growing noise. Then I saw the corrugated turbine cover rise and stand on end. Then I saw the rotor rising from underneath it. It was spinning. I could not believe my eyes. It rose about 3 meters. Rocks and pieces of metal went flying. We started to dodge them. At that point, the corrugated cover was nearly at roof level, and the roof itself had been destroyed. I made a mental calculation. The water was rising, 380 cubic meters per second, so I took to my heels and I ran for turbine 10. I thought I wouldn't make it. I climbed higher, stopped, looked down, and saw everything getting destroyed. Water coming in, people trying to swim. I thought, someone must urgently shut the gates to stop the water, manually. Manually, because there was no power. None of the protection systems had worked.
The formal report, which was released in October of 2009 by the Federal Environmental, Technological, and Atomic Supervisory Service, notes the cause as a result of fatigue damage of the mountings of Turbine 2 caused by turbine vibrations. 6 nuts were missing from the bolts securing the cover at the time of the accident, and of the 49 bolts recovered during the investigation, 41 had fatigue cracks and 8 of them had fatigue damage exceeding 90% of the cross-sectional area. So these bolts, they were in really, really rough shape. Like would be similar to if you owned a number of cars, say 2 or 3 cars, if all of your lug nut bolts had fatigue cracks or they had 90% damage on cross-sectional areas, like you would have all of the wheels falling off all 3 of your cars. The report noted that Turbine 2, which was controlling the output of the plant, i.e. would ramp up as required to meet the required capacity, while the other running turbines operated at a constant output. At least that's how we understand it. So it's basically, it's kind of the load turbine, so it would deal with load fluctuations. As mentioned earlier, the plant serviced large aluminum smelters in the area which had rapid and unpredictable load changes that the plant needed to adapt to very quickly. Because Turbine 2 was the turbine that was regulating capacity, its output was continually fluctuating, and at the time of the accident, it was operating in the non-recommended power band, leading to higher vibrations. Also noted in the report, there was a fire at a different power station that broke communications and automatic driving systems for other power plants in the region. The other plants would typically regulate output for the region, but with these plants offline, this responsibility was shifted over to the Sayano plant. And there seems to be some disagreement between the report and the company who designed the automated safety system as to why the turbine water gates didn't close automatically.
So that formal report was removed a few months after it was published, and unfortunately we weren't able to find a copy, but we did find several summaries of the report contents, and there seemed to be a lot of conflicting thoughts on why this turbine failed. So one article we found agreed with the fatigue failure of the cover as one of the causes and theorized that a generator short circuit could have been to blame for the failure of turbine 2. Other articles suggested that water hammer pressure lifted the turbine cover, and one interesting article provided an alternate hypothesis of the cause of the failure. So I thought that a continuous flow of water would pass through the turbine when it was running. This is how my brain thought turbines worked before I read this failure. So I thought that you just let a continuous flow of water through the turbine and it would run, and a set of gears would control how much rotational energy would transfer to the generator, which is kind of like how a transmission in your car would function. Your engine spins relatively at the same speed. I mean, your RPM can fluctuate, and your transmission couples and decouples different sets of gears to spin your wheels at different speeds. That's how I thought this worked. But in reality, at least for this turbine, there's gates on the turbine, and those are called wicket gates. And those control the volume of water that pass through the turbine. So the turbine's speed is directly related to how much water is flowing through it, and these gates control that flow. So when the load dropped, the gates closed suddenly, which stopped the water, but the turbine wasn't done spinning because it doesn't stop spinning that fast. It takes a few seconds to slow down. And so that created what is known as water column separation. So the gates shut, the turbine's still spinning, the water flows away from the turbine and creates a vacuum behind it because there's nothing to fill that space after the gates. Then the vacuum collapses the tube, the water equalizes, comes back up the tube, and collides with the underside of the turbine. So this article pointed out that the formal report didn't address the failure of all the other turbines at the station, other than to say they flooded. So several turbines were damaged, not just flooded from all the water in turbine 2, but they were actually physically damaged, and we're going to get into the summary of that in a second. The report also didn't explain the source of the upward force that would blow off the cover. And so this article theorized that it was this water column separation that was caused by the gate shutting off really quickly that created enough upward force to blow off the cover. So similar to the other failures we've covered in Russia, like Chernobyl and the Kursk submarine, even when there's a formal investigation, it often creates more questions than answers, and it's really hard to understand what happened and believe the report. That said, even in a perfect scenario with full transparency, it's also really hard and really challenging to know for certain what exactly occurred at the time of a failure like this. And so oftentimes these types of investigations seem to include varying degrees of speculation and assumptions based on how things were designed or how they were traditionally operating or how they'd be expected to operate, because no one has a crystal ball and could see exactly what was happening. So there's usually some type of speculation, but this one seems to have a little bit more than normal. But I do think, even though we don't really know for sure what happened, I do find all of the different conflicting thoughts and ideas about what it could have been that caused this to be almost more interesting, because you're seeing all these different perspectives. And yeah, I would say that the water column separation seems like the most plausible to me, but I'm not qualified to say what caused this, because this is well outside my area of expertise.
So as for the aftermath, it took about a week to pump water out of the machinery hull and another 4 days to complete the rescue mission. As we mentioned, 9 of the 10 turbines were destroyed. Turbine 6 was flooded, Turbine 5 had flooding and electrical damage, Turbine 3 and 4 moderate electrical and mechanical damage, some damage to the concrete structures around them. Turbines 1, 8, and 10, they had severe electrical and mechanical damage, as well as some damage to the concrete structure around them. Turbines 7 and 9 were completely destroyed with extreme damage to the concrete structures around them. Turbine 2 was destroyed completely, including the concrete structures around it. So all of these turbines took a large amount of damage, whether it was being destroyed completely or just flooding. Like, these are not turbines that you can just turn off and turn back on and they're going to work again. Like, they are going to need substantial repair work or replacement before this power plant can be operational again.
Well, and that's why I find it so interesting that the initial report, which we didn't read, but the articles that I did read about it claimed that it only talked about turbine 2 and not about how or why all the other turbines failed. But to see a significant amount of concrete damage around several of the turbines suggests that there was internal failures with those turbines as well. If there wasn't, you should just see flooding and electrical damage at all turbines except 2. At least in my thoughts, that would be the case. I mean, you're going to see a lot of water coming in because you flooded the entire machine hall. So it is possible that that would have caused that concrete damage. But also the number seems weird because you assume they go from 1 to 10. So if 2 failed, then why was 6 only flooded, but 7, 8, 9, 10 had severe concrete damage? That just doesn't make sense to me, which is why I wonder if when Turbine 2 failed, it took down the whole plant and all the wicket gates shut, and that's when you started to see that similar water column separation happen in some of the other turbines. That seems like a plausible explanation.
I would also go that route where, even though turbine 2 is the initial turbine that fails, if there's any sort of load sharing or load shedding that's happening in this plant and the other turbines are supposed to pick anything up, or there's components that are going into these turbines, yeah, I think that turbine 2 is probably just the impetus of all of these turbines failing, and then once one goes, it's just like a house of cards. One card falls and everything gets damaged. Because, yeah, like Nicole said, if this was just a flooding incident, I think you'd probably expect, electrical damage, obviously, maybe some issues, related to water damage, on the exterior. This wasn't salt water, so it's not corrosive. But yeah, I would largely expect electrical damage, and then, any sort of damage related to just the water sitting around too long or getting into areas of the turbine that it shouldn't be in. But certainly not multiple turbines, being completely destroyed or, other ones having, severe, damage that's not just electrical damage.
Well, and if it was the case that turbine 2's failure caused the others, then you'd think the ones closest to turbine 2 would have the most damage, and the damage would get reduced as you get further away from turbine 2. But that doesn't seem to be the case, which is just weird. Our notes say that power was fully restored to the area 2 days later on August 19th, 2009. And full disclosure, I can't remember exactly how that happened. The turbines obviously were not back up and running in 2 days. I think some of the other plants came back online and filled in the gap that this plant used to provide, or they had some other type of backup generation power. The turbines were definitely not running 2 days later. Because of all the flooding, there was also an oil spill that happened, and that's not surprising because electrical transformers usually have some type of oil in them, and because this was such a large power plant, there's a lot of transformers and they're large. So 40 tons of oil was released, and that oil made it all the way downstream as far as 80 kilometers from the dam. The Russian government paid just over $31,000 to each of the victims' families and just over $3,000 to each survivor. And the power plant's owners also doubled that. So that was what the government paid. The owners doubled it. The owner of the dam also bought housing for 13 families with underage children, and they created programs to help with school and higher education. And there was also a program to rebuild the main settlement where the power plant workers lived. As of November 2014, the renovations and repairs were completed and the power plant was put back online. So that was a little over 5 years it took them to rebuild it. Only turbines 5 and 6 were repaired in place. The rest were dismantled, taken out, fully rebuilt in a factory, and then replaced entirely. And the estimated repair cost was $1.3 billion. In 2017, new control and safety equipment was installed at the plant. And that is unfortunate that they didn't do that when they replaced the turbines, because that would have been an excellent time to upgrade the safety equipment that didn't work properly when the dam failed.
I also agree with that. So there you have it, the Sayano-Shushenskaya power plant failure in 2009. An underdesigned structure, erratic load conditions, and operating the system outside of ideal conditions led to catastrophic failure of nearly all 10 turbines and a 2-day blackout.
For photos, sources, and an episode summary from this week's episode, head to failurology.ca. If you're enjoying what you're hearing, please rate, review, and subscribe to Failurology so more people can find us. If you want to chat with us, our Twitter handle is @Failurology. You can email us at thefailurologypodcast@gmail.com. You can connect with us on LinkedIn, or you can message us right on our Patreon page. Check out the show notes for links to all of these. Thank you to everyone for listening, and tune into the next episode where we'll talk about the Fernie Arena ammonia leak in 2017. Bye, everyone. Talk soon.